Okay, so we've just heard about some really cool crossovers and results that we've been able to get recently in radio transient world. So I'm going to focus mostly on the future, what we're going to do with LOFAR. So I am very biased. There are a lot of other telescopes, but I'll also touch on the sort of further away future, which is the SKA. So as I said, I'll start with LOFAR. This is the very center of LOFAR. It's made up of 6 stations, and we can collect at the high band, which is 100 to 200 megahertz, or in the low band, which is 10 to 90 megahertz. It's not just this is about 300 meters diameter, but actually LOFAR is a radio telescope that's the size of Europe. Now, using all of the European stations has been quite challenging in the past, but we're working on that with the latest upgrade. But I thought it was just worth stating what LOFAR is. So you may know, or you may not know, LOFAR is currently turned off because it's going through a massive upgrade. But this is the sort of old LOFAR. And as I said, we have high band and we have low band. The high band, over the last 10 years, we have worked really hard and we can now calibrate and image this to very high quality. Low band, it's a lot more difficult. The ionosphere is a real pain down there. But it's something that we're going to work on for LOFAR too. The other thing shown at the top here, we could either use the low band or the high band. So, it was one mode or the other. Or you could only use half of the antennas that we had in the low band. So we wanted to change that, and we actually, through a range of special funding things, we've actually got to the funding to do LOFAR 2. And one of the biggest things is that we can use all of our low band antennas and all the high band antennas at the same time. And that's pretty awesome for if you want to do studying of light curves where you've got high band and low band at the same time. But for something that I'll show you later, being able to have the low band all the time is actually really, really useful. The other key things, Iris mentioned that we have a rapid response mode on LOFAR. It was about 5 minutes, which is pretty rapid, okay? But for a completely software-driven telescope, that's actually quite slow. So with the huge improvements to the system, we're actually expecting to get to 1 minute response time. So that's going to be pretty exciting if you expect coherent transients after your transient event. The other thing that is really important that's coming are fully automated pipelines. So in the past 10 years, if you wanted LOFAR data, you either had to learn how to process it yourself and have a massive supercomputer to do it on, or be friends with the surveys team. With LOFAR 2, the first calibration and imaging steps can be done for you by the radio observatory. And the goal is that all of the processing steps you can just have done for you to high quality by the observatory. Now, obviously that's going to take a little while, but it's hopefully lowering that barrier to getting into doing radio astronomy. So Iris already mentioned this a bit. We're doing a lot of unbiased transient surveys to try and find radio sources that we didn't know anything about. Oops. And this is the sort of population of radio transients that we know of. So on the y-axis, we have the luminosity of the source. On the x-axis, we have a strange unit, but basically it's 1 second or seconds, so time at 1 gigahertz, because there's a frequency dependence. Roughly about here is 1 second, and everything to the left, where your historical fast transient, and everything to the right was your slow transients. But actually what's more important is this dividing line here. And what you have on below that line are your classic synchrotron afterglows and that type of emission. And above that, you have your coherent emitters like your pulsars and your fast radio bursts. We also have that cool new population that Iris mentioned earlier in that black box. These have only been known for about a couple of years. It's thanks to very fast imaging surveys. So a lot of what we're doing with LOFAR is going from roughly a second up to months and years after. Should probably note, GRBs and AGN, they are not coherent transients in this plot. What you're seeing is a relativistic effect. So just, you've got time dilation there. So, as Iris mentioned, we had this amazing LOFAR survey, which was going around and taking 8-hour snapshots of the majority of the northern sky. And what you can then do is do time slicing and get very short duration transients. So we obviously have the one that Iris showed earlier. But we now have a team looking through the rest of the survey, because Iris only did a few %, and we're hoping to find a lot more things. And this is the sort of thing that we're doing. We're taking data that other people are observing and hunting for transients in them. To hunt for transients, we need a pipeline. Now, there are a lot of pipelines being developed for very specific cases, but what we've spent the last 15 years working on is the LOFAR transient pipeline. And basically, this goes through, measures sources in your images, does source association, and builds light curves. Now, as you can probably imagine, the pipeline was designed 15 years ago, published 10 years ago. It was all in Python 2. It was heavily reliant on its database. It was painfully slow. So we're now doing a massive rewrite by a team at Astron, led by Timo, and we're keeping the same fundamental idea. What we want to do is build light curves. Once you've got the light curves, then you can implement whatever exciting methods you've got to find transients and variables. So logic stays the same, but it is already, I think, I did an equivalent run with our old pipeline that I had to leave running overnight, and it took over 12 hours. And the new pipeline, it took about half an hour. So big improvement. And it's now going to be one of the LOFAR 2 supported software packages. So in theory, you can ask for this pipeline to run on your data, but it's also going to automatically run on the large surveys that are going to be running by LOFAR. And that's thanks to the fact that they're going to be running the first processing steps, and then we can jump in. So basically, you get your data from your radio telescope, you have to do some sort of calibration, and then you can get a clean, deep image. We also have our equivalent of image subtraction, but instead of subtracting from the images, we take our sources out before we make images, and that's because we're using a Fourier transform of the sky, so we can do this quick step. So in LOFAR 2, we'll be creating those 8-second images automatically. These will then go into our transient pipeline and produce this light curve database. The reason why this is so important, this is going to become publicly available on the LOFAR Science Data Center, and we'll make sure that the database is VO compliant. There will obviously be a proprietary period for the main database, and for the snapshot images, we'll have to do a bit of cleaning because we get quite a lot of artifacts, but the goal is, for the first time, these things will be publicly available from our team. But there's a problem. So it takes about a week for the data to get from the correlator, so the main computer in Groningen, onto the Science Data Center. Then calibration and imaging at LOFAR frequencies is really slow. Even that first step will take days. and it could take days to image. So you will be finding out about your transients a few weeks after the event actually took place. Now that is amazing compared to what we've been able to do so far, because it's usually been years afterwards, but that's not the dream. And I did some work with, well, now my PhD student, Lars Van, and Jason Hessels, who some of you may know. And we actually said, well, do we need to calibrate the data? Because that's the thing that takes all the time. And what you have here is images of uncalibrated LOFAR data. So it looks pretty ugly. There are a lot of artifacts, but the trick you can do is that those artifacts, yes, they change with time, but they change of order sort of 30 seconds or a minute time scale. So if you do it really fast, you can subtract one image to the next. You might get some artifacts, but actually it's pretty clean. And Iris showed you a transient earlier. This is the same transient in uncalibrated LOFAR data. So it's in that green circle. So that means we don't need to take days to calibrate. Jason Hessels also has a supercomputer that's going to be plugged in next to the main LOFAR computer and get the data in real time. So in about a year from now, we hope to have real-time radio transient detections. Now, these may not be reliable, so to start off with, we will want to do some work to make sure that what we send out is reasonable. But for the first time, I think we can say we're finally getting there with radio transients, getting to a similar level to the rest of the multi-messenger community. But one thing that would be really cool is to do imaging of the whole sky. Because, okay, I need to really speed up, because a lot of our transients are not well localized. So we actually had a whole sky imager. This is a very sped up movie. We see planes and satellites, and we have a way to quickly filter those out. But it means that if you have a poorly localized event, you can trigger on it. But this only worked when LOFAR was in that low band mode. So only a few % of the observing time could we actually observe. We did find some cool transients though. We're trying to figure out what they are, but we'll see. But I managed to bring in an ERC grant. We're going to actually get better images. So this is a whole visible sky image on the left from sort of an early version of this telescope. Our resolution is pretty poor, it's 30 arc minutes, but it will be operational whenever LOFAR is turned on. Now, we can't we can't process that data quickly enough because we're producing a few hundred terabytes of data a day, but we will have a 24-hour buffer. So if a gravitational wave event goes off, or a neutrino event, or your favorite transient, we can, if we know within 24 hours, we can dump that data and look for a radio counterpart. And that means that if we're chasing things like coherent emission from a gamma ray burst, LOFAR will be able to target all of that different emission, combining these instruments. I don't have much time, but coming, we have the next generation of radio telescopes. We have SKA low, which is operating from 50 to 350 megahertz. And you can see the, well, here is an example station. These Christmas trees are the antenna, and the array layout is up at the top. We will also have SKA mid, similar idea, but at a few gigahertz. And the key thing is this is the first SKA mid dish being lifted into place. The key thing is the timeline. So we're currently for having construction, and for low, we're already starting commissioning. But the key thing is here, 2030, the first SKA low data will be coming. So we can actually start following up transients, searching for transients. For mid, it's a couple of years behind. And this, also shamelessly stolen from the SKA websites, I've highlighted where we can actually do TOO observations.